Hello, my name is Philippe Kerbois. I'm the glass lead at Techland, and I would like today to introduce the in-furnace imaging survey of a float furnace for combustion optimization. I want to acknowledge Neil Simpson, who will introduce the results and the benefits of using the NIR-B technology for combustion optimization in the float glass furnaces. This year will be also impacted by the travel restriction due to the pandemic, and we would like to apologize not to be with you face-to-face to discuss about the specific job we are going to present. 2 years ago, an independent float glass manufacturer had an environmental emission challenge using true port gas burner. They initially approached Neil Simpson combustion. In fact, there were a marginal improvement following several visits and basic furnace optimization, but no adjustment could change the flame shape for one burner. A new gas nozzle design was manufactured. In parallel, a 5-day Techland in furnace near-infrared thermal imaging survey was performed. It's believed that this paper will be the first introduction of in-furnace thermal imaging in a float furnace, and he also believes that this is the first presentation of in-furnace thermal imaging with the inclusion of regenerators. First time. 3 days were allowed for the baseline survey. However, the on-site customer support enabled the task to be completed in 2 days, allowing for an additional day to undertake the burner in furnace optimization. The regenerator thermal imaging survey highlighted a strange phenomenon whereby on the port, the flame could not be adjusted. A conventional photographic survey confirmed the lifting of the refractory but could not indicate the formation of the bypass flow. This paper will demonstrate how this thermal survey method can be used as a furnace optimization and a combustion development tool. And the final report and presentation to the float manufacturer and their local environmental authority justified continued work on primary emission reduction method as well. This is the 5th consecutive paper at Glass Problems. This year, we will present the in-furnace thermal survey with the NIR-B technology, which is the first time the results and benefits will be introduced for a large float furnace and probably for the regenerators. The equipment used are the industry standard legendary Cyclops C100, which is an handheld pyrometer for temperature measurements into the glass furnaces. Then, this will be reinforced by the transportable NIR-B glass thermal imaging system that is more than 300,000 Cyclops temperature measurements, where the final data will be brought in, providing thermal images. We are going to talk about the benefits of using an NIR-B in transportable mode, reinforcing visual inspection and optimization of combustion. But there is a real potential to use the NIR-B imaging systems on large float furnaces, especially with the new high-definition camera, 2K, 3 million pixels, for fixed locations. Knowing the systems are providing repeatable thermal distribution and very good images based on improved field of view, we could implement such system on 3 main locations described in the sketch, where the arrows represent the NIR-B cameras with implementation angles. Please consider the 2 sides are equipped. We could use on imaginary port 0, which provide a very good view on ports, arch and flames, or imaginary port 7 for improved view on flames and ports, or on the bridge wall center line of the furnace. Other locations are possible as the traditional approach on charging hand both sides. The key point anyway is to reinforce the temperature measurements, the isotherms, balancing the coldest and hottest points, the flames optimization into the furnace, combining the batch control with automation 4.0 in a permanent way. And not only. There are many possibilities to use the NIR-B transportable system for the thermal surveys. Generally, as described in the sketch, the main interest is to use the existing peoples all around the furnace, including left-hand side and right-hand side for bridge wall and waste. The regenerators both sides as well could be investigated. Ideally, we capture firing left and right with a recording with the 2 last minutes of firing. Point where flames goes out till flame on. Need to capture firing right to left and left to right. Based on the 4-day job, 4 initial locations should be investigated. The doghouse, or port imaginary 0, to see waste and both sides. Bridge wall, based on high people's location both sides, but the most important here. Regenerators, typically 7 locations, including both ends if possible. I'm going to introduce and comment some basic images coming from this thermal survey, and we'll let Neil Simpson to go further with details and benefits for optimization. Here is the first initial test point, safe and easy access. That is the PEEP side refiner left-hand side to check system fully operational. The image is good and clear and consistent with optical perimeter. See visible damage at crown joints. This image was created with the previous LEAP software replaced by the new ImagePro Glass software from LED. Same image created with the new ImagePro Glass software. This is a larger image for more clarity and details. ImagePro is fully compatible with existing NIR-B 656 standard definition or 2K high definition cameras. PEEP side, refiner left hand side. See the really cold areas for acid condensation, possible air ingress. Same image created with LIPS combined with zooming shots for lateral locations. The new ImagePro software is able to provide an image with a 62 color isotherms palette. Interpreting this image shows clearly a rat hole thanks to the 62 isotherm palette as well. We use the zoom function with ImagePro up to 800% for rat hole location with the isotherms based on 1388 degrees C with the red color. We could use the 5 isotherm functionality showing gradient temperatures with 5 different color bands.
This is Neil Simpson. I'd actually been supporting this customer since 2016. And so the overall purpose of the survey was to come in and look to do a thermal survey, to look at it from an asset protection perspective, look at sources of parasitic air, and to focus on the thermal profile, both from an energy and also quality problem. And then ultimately, the main reason for doing this was looking at the flames with a view to try and reduce the NOx. Mark Briggs and I spent 5 days on site in 2019 taking measurements and optimization of the flames. I stayed for a further 4 days and prepared a 467 slide package which the customer ultimately presented to the local environmental authority. The goal was really to demonstrate the benefit of the NIR-B and thermal survey, give an extensive report for their local EPA, see if there's any areas of parasitic air. Typically we can get 3 to 5% energy reduction if those are repaired. Obviously lowers cost, lowers NOx, and then potentially reduce flue gas temperature and volume. Wanted to confirm the thermal profile because in the past when they've been on low iron there was a risk of getting defects on firing on one side, and ideally here look at where we could see where the NOx is being generated with a view of attempting to reduce it. The original plan was to have 4 days of doing survey and then 1 day of optimization, but the support from the site guys was so good that we actually managed to do all of the survey in 3 days, and so we had the chance to spend 2 days doing optimization. Now, Philippe's already shown the initial images that were taken in order to make sure everything was okay with the camera setup. This was literally the first image that was taken from the waste peep hole. And at this point, I'm using the isotherms where the red is the coldest and the blue is actually hottest within the pallets. Anything in red is below 1388, and so there's a risk of sodium hydroxide condensation. We tend to see where there's all possible sources of parasitic at this point. The thing that really did surprise me at this point was how cold the charging wall is. That wasn't something I was expecting to see at this point. This is the first frame where the flames have gone out after firing from left to right. Now left is shown here on the right, so I'm looking in terms of the flow of glass. The red mark indicates the hottest point in the furnace, so that's between port 3 and port 4. And looking at the charging wall, what I'm pleased to see is that the recirculation seems to be more or less in the center of this. At this stage, I've gone on with 150% zoom, and I've added new 10-degree isotherms. So at this point, the blue is cold and the red is going up to hotter. So the blue is 1430 to 1440, going up to then being 1470, red being 1470 to 1480. So it confirms that the recirculation zone seems to be on the furnace center line. We can see where the batch line is. You can see possible foam. This is something we often see at the end of the firing side, so some foam underneath the burner. And then alarmingly, we see some pretty significant port damage on the tuckstone at port 5 at this point. The same view, but I've increased the isotherms by 50 degrees. The port necks are clearly colder than the breast walls, which is good to see. So the flames are not too hot, and also looks as if in addition to damage at port 5, there's also damage on port 4. Another plus 50 degree isotherms. So we're starting to see the symmetry around the hotspot, which is again something we typically see. The reflection on the glass is always colder than the foam because the glass absorbs the heat. Clearly the port necks are all colder than the breast walls, and we're also starting to see the hotspot reflection on the immediately previous firing side. So left hand side, you can see a little bit of reflection there. Now this is the last of the isotherms, and so we can clearly see the hotspots. It's between port 3 and port 4. Now it was historically believed to be at port 4, but that was just a spot measurement taken using a Cyclops. Reality here is the image we see is being taken from 324,000 thermal points. What we can also see is probable foam layer underneath the hotspot. And this is a new palette that Land have developed, and basically it's 62 isotherms. And so I've set these so that each color is 3 degrees. So it's 62 times 3 degree isotherms, and that really summarizes all of the preceding slides. And you can see the center of the recirculation. We can see the hotspot. We can see the batch line, the foam issues on either side, and also the tuckstone damage at port 4 and port 5. Now this is a view inside the regenerator on the right hand side. Whilst it's a 6-port cross-fired furnace, there is a wall between port 4 and port 5. So there's 4 regenerators, being 1 to 4, and then 5 and 6 were as a separate compartment. To the best of my knowledge, this is the first time anybody ever presented a thermal image inside the top of a regenerator. We can see clear damage to the skews, and certainly somebody is going to be scheduled to come in and do some ceramic welding on these. But I've shown the ability to actually have virtual thermocouples. So I've put virtual thermocouples in each of the port necks, so port 1 being the closest, so 1, 2, 3, and 4 going down, and then showing how you could have a corresponding thermocouple, virtual thermocouple on the target wall. Now I've shown these as simple points, as you would expect. Equally, these could be larger areas as well, and it gives an indication of the table of the fact that you would be able to get minimum and maximum temperature, especially if it's a bigger area. Now, since one of the visits I'd made in February 2018, I knew that there was a problem with the port 4 on the right hand side. Now these are water-cooled 3-port burners, gas, so twin nozzle. I was involved in the original development of these at Laidlaw Drew, and it was one of those things that it didn't matter what I tried to adjust the burner, it had no impact on the port 4 right-hand side flame. Foswell had been in, and certainly it corresponds that there was a strange heaving or lifting of the refractory checkers, and certainly I've never seen anything like this before. And this is a view of port 4 taken from the target wall, and looking across you can clearly see the through-port burner raised, and you can see the hotspot on the flame. So we're looking from behind the flame at this point. And you can see in the lower right-hand corner the cold spots, and it's pretty significant damage. And this is the view where I've zoomed in 150% to get a bit closer view. We're on the exhaust side, so we're looking into the flame that's coming towards us. You can see the flat flame effect. Strangely, what we're seeing here is the hottest flame is actually from port 3, so upstream, it's where the X marks the spot. But you can see down in the right-hand corner, clearly there has been significant movement of the refractory. Surprisingly, they appear to be lifted. I've seen lots of collapsed checkers in my life, but I've never seen anything that appears to have levitated and gone upwards. On previous visits, I've been able to identify that it was the port 5 burner that had the highest NOx. We looked at trying some different designs of nozzle to go in there. On the 22nd, we optimized the fuel profile, and then we subsequently went in and installed a different design. That was initially firing from left to right, and then on the final day, on the 23rd, we made the change firing from right to left. So both burners then had that design. And so this is a look at port 5 firing from left to right, and this was what we'll call design A. And at this point you can see with the larger image that the flame is almost square and not really flat as required. Look at top right hand image. You can see that it's visibly hot by looking at the palette we have. And then finally, bottom right hand corner, being able to split out and specifically look in at different temperatures by applying different isotherms in here. Clearly, we don't know the emissivity, but these are just relative comparisons of temperature. And then this shows the design B, and this is a far flatter flame, as you can see, much more as designed. Looking top right hand corner, it's certainly it's got so much whiteness to it, and again looking at the same isotherms, the flame is colder. So on the left hand side here, we've got the day 1, and this is with design A in port 5 on the right hand side. And then the right hand column, we're looking at day 4 with the new design B. And so again, similar ranges, and it's quite evident that on day 1, the design A flame was significantly hotter, whereas if you then look at the right hand side in both images, we're showing that the flame temperature is significantly lower. Again, similar orientation, left hand side being day 1 with the design A, and right hand column being day 4 with the design B. And you can see how the port 5 flames clearly were the hotter flames, and how much we've been able to reduce them. And for anyone who wasn't surprised with where we were going with all of this, reality is that even by just changing the design of the port 5 nozzles, we were able to significantly reduce the NOx over the entire furnace. So we managed to reduce by 10.5% on one side and 23% on the other.
This is time for conclusion. The NIR-B has identified some potential sources of parasitical air and refractory damage in furnace. some possible first ever thermal image inside regenerators, problems with region number 4 right hand side and explanation for combustion issues, demonstrated as well ability to see where NOx is being formed and provided a NOx reduced by 23% through optimization, and at the end a potential to use for troubleshooting quality. So thank you for your attention, and please feel free to contact us for any details or any job in the future. Bye bye.